Well, from 2.4, the main message of 2.4 was that in addition to looking at the equilibrium distribution of saturations within a profile that we had thought about in things like this geometry here, which really relies only on the capillary pressure versus saturation curves, which allow us to say something about the distribution of saturation within the column, both within this smeared column and also within the pool where it ends up. We can also say something about the rates at which fluid might flow through places where there are two fluids present. One would be a non-wetting fluid, which would be this napple, or it could be air in some cases, and the other one's a wetting fluid, which is typically in quartz, sand-like rocks, is typically water. And so those are the concepts that we talked about last time, defining the rates at which we could expect flow would occur through this particular system. How do we calculate what they are? And we know that we do it in terms of what we call relative permeabilities. And so, as usual, today we'll maybe try and nest those concepts together. In addition, we'll try and talk a little bit about what the permeability of fractures are. We said before that if you look at capillary pressure versus saturation curves, it's much easier for these fluids to get into fractures and keep on going than it is to get within the permeable material. And so understanding what the permeability of fractures might be is useful, because those are primary paths for transport. And also, it may well be that we can link concepts of permeability and capillary pressure saturation curves together, maybe because we can very easily measure permeability in situ through pumping tests. Maybe we can use that information to say something about the capillary pressure behavior of both fractures and porous media. And so that's really the goal of what we'd like to talk about today, which is this one here. We'll spend most of our time on that. There are ways of looking then at combining all of these concepts into understanding how multiple fluids flow in the subsurface. We can define governing equations, mass balance, conservation of mass equations, which is why you've had that prior in your background, to be able to develop models that basically differential equations that prescribe that behavior. And then we can solve them in simple and conceptual ways, such as Buckley-Leverett equations, to be able to say physically about how multiple fluids will progress in the subsurface, because that's something that we might like to be able to define as a useful design component. So that's kind of where we're going today. So the bulk of our time will be spent on these three things after we recap our activities. Okay. This, let's see if I can get this. This is an amalgamation, if you like, of two figures that you've seen. You have in your notes, and it's probably useful just to take stock of the ordinates, if you like, the important ordinates on these two principal figures that we have. The first is capillary pressure versus saturation curves. And the second are relative permeability curves. Rel-perm curves, as some people like to call them. And the principal features are, I guess you should, this is capillary pressure, which by definition is always defined as the pressure of the non-wetting fluid relative to the wetting. I remember we did the lights last time, right? And they both scale on the base with respect to saturation of water. Saturation of water either runs from 0% saturation of water to 100%, and since it has to be filled, we know that the sum of the saturations have to sum to 1. And so the converse behavior is if you fill up with the non-wetting. So 100% water means there's no room for anything else for the non-wetting. 80% water means there's 20% of the non-wetting is available. So these define both capillary pressure and relative permeability. And we have relative permeability for the wetting. And relative permeability for the non-wetting. And these always vary between 0 and 1. And they vary between 0 and 1 because if we want to calculate, for instance, exactly what the volumetric flow rate is, we can define that in terms of flow within a tube where we have a pressure applied along the length of it and a cross-sectional area defined and a volumetric flow rate Q defined, if you can see these things. And it's always given by Darcy's law, which is an area, an effective permeability divided by viscosity of the fluid that's flowing times a change in pressure with length. And it's this effective permeability that we have here, which is a function of two components. It's a relative permeability and it's multiplied by a true permeability. And true permeability is when the behavior is measured when it's 100% saturated with one fluid. Doesn't matter what the fluid is. It could be air, could be helium, could be water, could be any Newtonian fluid. Couldn't be molasses maybe or cement, but this is the product of these two. And so this is really just a scaling magnitude. It is between 0 and 1, and it in some respects says something about how much of the pore space is available for that particular fluid to flow. And this, if this is the flow of the wetting fluid, for example, then this would be the relative permeability of the wetting fluid. If it was the opposite, if it was the non-wetting fluid, then we'd take the converse relative permeability. So that's all it is. And so physically, these relate to, in this particular case, I guess this is, the water is red. So 100% saturation of water means that only water is flowing. We know that because of the concepts of these relative permeability curves, that there are a couple of cutoffs. And the cutoffs are these magnitudes here. Doesn't quite go because they don't, I guess I could do it like this. And then take a jog over here and then just keep on going down here. And likewise I could do the same here, I suppose. This one actually is better aligned, so that maybe do it this way. And these areas here represent zones where physically what's happening. What's happening here is that, well, we should do it the left-hand one first. So you start off with something that's filled with water, you push napple into it, and so the proportion of the napple grows. So this is the saturation of the non-wetting fluid, and this is the saturation of the wetting fluid. I guess I'm keeping these colors consistent with what's down in the bottom. The red is water and the green is oil. And so that we know that once we've put this non-wetting fluid in and saturated it to as far as it can go, we can't get any more than this water out of the system. So it exists with, if this is 75%, then there's 25% of water that's left in the system that is then immobile. It can't move, and it's trapped in here. Once we then back off the pressure that's applied to this, it will spontaneously imbibe, suck water in, and come down this curve, but it can only get this far. And this far is where it resists with the irreducible saturation of the non-wetting fluid. Which we can call SNW0. 0 means irreducible. You can't get a saturation less than that. And this means that, say, 15% of the oil is left in here and can't be taken out, as opposed to this magnitude here, which happens to be the irreducible saturation of water. This is SW0. So the difference are that this is water that's trapped in the system. You can't get any more of the other substance in here than that. And this is the non-wetting fluid that's trapped in the system, and you can't get any less of it than that much either. And the consequence of this are that when you look at the relative permeability curves, then they change in this fashion, because if you're looking at the behavior of the non-wetting fluid, the green fluid here, you know that it's simply connected across from the left side to the right side, and so it can flow. The red blobs are not connected, and so you'd expect that the green relative permeability would be some finite number between 0 and 1, which is somewhere here. We do it as green. And the relative permeability of the red fluid is basically 0 because it's not connected from one side to the other. To get the red fluid to flow, you'd have to do something like, for instance, push more red fluid into the system. If you push more red fluid in the system, you're physically going in this direction. And you move from non-connected from one side of the domain to the other to immediately when it becomes connected, as in this case. And then it would start to, the relative permeability says that now it's connected, and in this intermediate portion, both fluids are flowing. So you have a pressure gradient on the upstream side, that's driving flow. Red fluids flowing out, green fluids flowing out. They're both connected from upstream to downstream. And the proportions at which they'll flow are given by these relative magnitudes. So if you find yourself at a particular saturation, which is here, say, then the relative permeability of the non-wetting fluid is this amount, which would be, let me do it in the right color, it would be the green, right? And this would be, I'm running out of space, but this would be relative permeability of the non-wetting fluid, and it's something like 0.4, right? And this would be the relative permeability which would be this, which is something like, I don't know, 0.05 maybe. And this is maybe 0.35 or 4. And so immediately these basically allow you to be able to calculate the flow rates that will come through this, if you know what the pressure gradient is that's applied between upstream and downstream. And in this particular case, I guess it would be something like this, right? This is dP, and this is dx. Does that go on the board? Yeah, just, right. And so the same thing. And so it immediately allows you to calculate the volumetric flow rates that go across the system. And that's really what we've been attempting to do. So this is useful in visualizing what it means, what these components physically mean as the limits between the irreducible saturations are. That's basically at these points, the two phases aren't connected across both faces of this flow region. Here only red is connected between upstream and downstream, green is not. And here green is connected between upstream and downstream, and red is not. I guess this one here. This is just as it makes that connection right at that point. So it's useful to think of these in terms of these curves used together. Some other quirks, I guess, of this are the fact that we have scanning curves. Scanning curves mean that it matters which direction you're draining the water out of the system and imbibing the water back in. So if you only come part way up here and then drop the pressure, then you go across on these scanning curves, and they're kind of non-unique. And I guess the other thing that is apparent here, that if you have a particular saturation, potentially, at that particular saturation, you have two possible saturations, capillary pressures. So in other words, if you're at a given capillary pressure, or if you're at a given saturation, you could be at two different capillary pressures, because both of these are valid. Or alternatively, at a given saturation, choose a place to write this, you could be at two different, at a given capillary pressure, you could be at two different saturations. So it's slightly non-unique. But the band of this hysteresis is pretty narrow, and so you could think of this just as a single relationship, which is, if you drew a very wide curve, then that single relationship could be this red curve that I'm drawing on here, which I'll remove. So if you ignore the fact that you have these fine black lines underneath this that describe this behavior, you could think of this just as in a band, and it's merely a consequence of hysteresis, that there's some uncertainty, if you like, between what the magnitudes of the saturations, capillary pressures might be, or what the saturations might be, just because of this effective hysteresis. So that's kind of summarizes, I think, what we talked about last time. So the important thing is this relationship here, Darcy's law. That's all it is. It allows, it allows us to be able to define the flow rates through the system if we know them. And I would say that the easiest analog that describes this conceptually is this behavior that we would have looked at last time, and that is this initial concept here, that you can think of it as a core where, instead of having the two fluids kind of distributed out within these tortuous paths within the pore space, imagine being able to centrifuge it somehow. So you have all of the red fluid in one place and all of the green fluid in another place. And basically then, if the porosity is homogeneous, then the proportions of these are a little bit like the saturations, because you could draw the relative permeability curves to look like this. You could draw the rel perm curves. And this is a bit thick for me. This is the saturation of water between 0 and 100%. And this is relative permeability from 0 to 1. And in our case, the non-wetting fluid was green, right? Water was red. So the green, you could think of this as the curve to represent relative permeability of the green fluid, and the curve to represent relative permeability of the red fluid. And so if you think about this, if the saturation of water is 100%, then all of this would be red. There'd be no green fluid at all, and the relative permeability would only be to the water that's going through the system. If it's all green fluid, then that means you're at this point here. The relative permeability of the non-wetting fluid is 1, and the relative permeability of the water is 0.
Are you assuming that all the pore spaces are cylindrical?
So this is actually a core that has pores within it. And so, so that's an important point. So this is a core that would have lots of tiny little pores, and the pores would be this size in here, dotted throughout here. And so it doesn't matter. It matters that the pores are all the same size probably, but not necessarily the same shape. So, and if you have an intermediate magnitude of saturation, which would be this value here, then all you need to worry about are the magnitudes of the relative permeabilities that come out of this. And so this would be 0.7, and this would be something like 0.3. And you notice here that in this particular case, if it looked like this, and of course if it doesn't quite look like this, right? The ones that we drew before looked something like, let me do it really finely. And so the diagram we drew before looked a bit more like, for the red, it looked like, whoops, didn't want to do that. Looked something like this. And for the green, it looked something like this. And before, if you added the values together for any particular saturation, for in other words, this magnitude plus this magnitude, so in other words, this red height here, it's getting a bit messy, isn't it? Plus this green height here, they don't add up to 1. But if you look at this X-shaped curve, by definition, because it's not quite true, not quite reality, they happen to add up to 1. But you can think about it just scaling with the saturations. So as you progressively fill more of the pore space up with the red fluid, then the proportional area that's available to transmit that scales with the saturation directly. And that's why these values sum to 1. So that's an imperfect way of describing it, but actually kind of a useful one. Imperfect because it's not true, right? It's not true because we know that these relative permeability saturation curves actually look like the ones we've just drawn. Okay, so that's kind of a summary that's taken us to link these concepts together of relative permeability and capillary pressure versus saturation curves. Let's look at what the real curves look like. So this is the curve that we've looked at already. And just to make the point that when we look at this, they're not X curves. So the X curve we had before would have been this and would have been this. It doesn't actually conform to what we see. What we see instead in terms of those two colors, I guess, would be the green curve, which is this here. Don't know if you can see that on top. And the red one. But if you add these two curves together, in other words, this height here plus this height here, then what you get is a point that's the sum of those two. This dashed curve here is just the sum of those two. It's very blurry, but this is Kr sub W and Kr sub non-wetting, and the sum of these together. So unlike the X curves, they don't add to 1. And the reason for that is that the entry into different pores is restricted. If you think about the pore spaces which these would fill up, then you can imagine that in a given pore, if the pore happens, so now not a piece of core, but this is one little pore throat, then we know that the behavior of these pores is that, first of all, the water sticks in a monolayer on the wetted side of the pore space, and inside that the behavior would be fully filled with this bubble of the non-wetting fluid, which is the green. This is the non-wetting fluid. So this particular behavior would be somewhere here, somewhere in this length here, because the saturation of water is very low, close to 0, and really even it's not really mobile, it's just a smearing on the surfaces of all the grains, of all the pore throats, that is continuous, I guess, as you go from one side to the other, but it's so thin that it's basically not chemically held, but it's held by meniscus forces on the surface, and there's no appreciable flow. The only flow that occurs on the bigger portion at the center. As you change the saturation of that, and you go from that initial behavior to, I suppose it would be something like this, with now a much thicker layer on the outside, and with the inside filled with this, you'd be somewhere here. So in this particular case, both the non-wetting fluid is really able to flow easily, and the wetting fluid is able to flow less easily because now it's just thinner. And as you progressively go across the side of this, then it changes from this particular behavior to, I guess, something that looks like, you know where this is going, right? So this is going to be this. And it's just going to be a blob in the middle. And so here both are mobile in this region, and then at some stage this gets just left in the pore space. It looks like the central conduit of a tube that goes through it, but we know from what we've looked at before, when we've looked at the different forms of these saturations, if we scoot back quite a long way, I think, to a figure that looks like this. This bottom one, this is in the same components. So this is very low saturation of water, very high saturation of oil, so-called pendular saturation of water because it goes around the grains in the rings. And so we're just idealizing it instead of a grain-grain contact where the oil fills up the spots between the grains. We've had this tube which represents the central core, which is green. And as you decrease the concentration of the oil or the saturation of the oil, this green blob in the middle ultimately is not connected, it's just a bubble. It's not a gas bubble, but it's a liquid bubble that sits in the middle, and it is no longer connected from one side to the other. And so those represent the behaviors that we have. And so understanding that, I guess, is the key of what we're attempting to do here. So the features of these relative permeability curves are given in these three figures. The key ones that we talked about are that we know that if you add these relative permeabilities together for real rocks, they don't sum to 1. And the reason that they don't sum to 1 is that the pore spaces are filled differentially with the components. And they don't most efficiently fill the pore spaces we've alluded to in the fact where you kind of centrifuge a core and you get the green fluid in the bottom and the red fluid in the top, and that they're uniformly distributed. The second case is that the relative permeability of the non-wetting fluid at its irreducible saturation is typically higher than the relative permeability at the irreducible saturation of the non-wetting fluid, which is this amount here. And that's because this non-wetting fluid takes up this central portion of the core of the pore, which is a higher rate, a higher diameter, if you like, than the efficiency of the stuff that's around the surface. And so this magnitude here is typically higher than this, typically by a factor of 2. So that's a quirk of the behavior. A consequence of hysteresis, which we looked at in the capillary pressure versus saturation curves, the fact that we cross over from a drainage curve to an imbibition curve because of the direction in which saturation is going, you could imagine would also have some effect on the relative permeability curves. And that is that if you're draining water out of the system as you go up this curve, then relative permeability changes in a specific way. If you're then imbibing water back into the system, then you don't actually track back along this curve, but it's a slight offset. And that's a direct consequence of the same behaviors that we saw when we looked at capillary pressure saturation curves, the hysteresis. And, well, I'm not going to worry about it. The form of these curves also changed dependent on the pore throat distributions. And so you can imagine that if you have not a uniformly graded material where all the pore throats are the same size, but you have some populations which are small and some populations that are large, you know that the large throats will preferentially take the non-wetting fluids because of these arguments that we talk about here, that they can more easily get in the cores of these larger core throats, because they can get entry to those at lower pressures as they're pushed into it. They have lower entry pressures applied to get them into it, and so preferentially, hence the reason for this relative permeability distributions, and also the fact that we end up with curves that will change in shape depending on that pore throat distribution. So that maybe brings us up to combining our thoughts of relative permeabilities from the discussion from last time. The main features that will allow fluids to go to depth in the subsurface of fractures, important. So maybe it's possible for us to say something about the permeabilities of fractures in the same way that we've tried to put together capillary models for porous media. And so the idea then is that you take a feature which represents the flow conduit, and instead of being a capillary tube that has some radius that we're able to push things along just like a pipe, it happens to be two parallel plates with a gap between them. And within those parallel plates, we know that if you look at flow within here, the flow is anchored to the wall of this fracture at each of the upper and lower boundaries. And so if you look at the velocity profile across it, then the velocity is 0 at the upper boundary, 0 at the lower boundary, and actually has this parabolic form between them. And if you solve the Navier-Stokes equations which give you that behavior, and it has this parabolic form which is given by this. But if we want to know the amount of fluid going across here, what we need to do is just find the area under this curve. And so what we can do is we can integrate this area under this curve, and that gives us, if we know individually the velocity at any particular point, if we multiply that by some magnitude, let's call it dy, if this is the y coordinate, then some small little differential height is dy, and if we integrate this, we end up with q, right? So now physically what that represents is just this hashed area underneath this curve. So this is the volumetric flow rate, and then if we take this q and we divide by the width of this fracture, this gives us an average velocity. So it's the same as converting this parabolic distribution of the velocity to something that actually looks like this. And so that's a bad rendition, but this area under here would be the same as under this blue curve here. That's it. And if we do that, we won't do the math, but the math is that the average velocity is equal to gravity, the square of the aperture of this fracture, the spacing between the walls, the kinematic viscosity, which is nu, which is just a dynamic viscosity, which is in pascals per second usually, the one that we usually use, divided by density, which is in kilograms per meter cubed, for these two terms. So it's a different unit than dynamic viscosity, and a factor 12. Just turns out to be that. So what we could do, if we wanted to, is figure out exactly what the flow rate would be in a single fracture. But typically we'd have these in some kind of formation where they're spaced between individual fractures. There's a spacing between the two walls, which is where the fluid flows, but then the next fracture will be located somewhere relative to that, and let's say they're parallel. They often occur in sets. So if you look at the road coming down on 322, where you might have done your GSI 101, then the fractures might look like this between the two walls, and they might have other cross fractures going across them. And this is the structure where we like to figure out exactly what magnitude of fluid rate occurs within these individual features that cross between the limestone, in the case on 322, which is relatively low permeability. So what we could do is, if we know what the permeability is for one fracture, then we could actually put it together so that we take the permeability, the flow rate in one fracture, and multiply between the flow rate, which is for one fracture here. So in other words, This is the velocity in one fracture. If you multiply the velocity in one fracture by the aperture, B, this becomes cubed. And so this now is a flow rate. So this equation here is just this multiplied by B. And this is the flow that occurs in one fracture. If we look at the number of fractures you have in a 1 meter length of this, if the fractures are 0.5 of a meter apart, there'll be 2 fractures per meter, right? 1 over 0.5 is 2 fractures per meter. And so what we could do is we just multiply Q by the number of fractures we have, which is 1 over S. So Q for one fracture times the number of fractures is equal to the total flow rate for all the fractures. That's really all we're saying. And that's what this really is. And so the flow rate in one fracture is this amount, the black bracketed terms here. And the magnitude for the number of fractures is this bracketed term here, 1 over S. And so it doesn't really matter how we derive it particularly, but that's the mechanism. We know how much flows in one fracture. We know how many fractures there are per meter, so we can calculate what the flow rate is that represents kind of the average volumetric flow in a given, what we'll call REV, representative elemental volume. And it turns out that the equivalent hydraulic conductivity, KB, uppercase K sub B, is just equal to this. And the reason why it is this, we switch from being 12 to this, is that if you look at the flow in one set of fractures, hello, which is this, then the flow rate is given by this magnitude, which is a factor of 12. If we then superimpose on top of that another set of fractures, and I'm not going to be able to do this very well, and if the spacing between these is exactly the same as the others, so in other words we have a structure that looks a bit like this, where these are just, the spacing between these fractures is S in both directions, then we have, if we're looking at flow into the board, you have flow along the blue set of fractures, which is equal to GB cubed over nu times spacing. I'm just taking this. And the component due to one set of fractures, if you like the blue ones, is going to be 1 over 12. But the component due to the green ones, which will be additive, is going to be 1 over 12 as well. And so if you add these two together, you get 2 over 12, which is the same as 1 over 6. And so the reason that this expression is slightly different from this is just that it's for the blue ones and the green ones going in the same direction. Yeah.
The friction taken into account with permeability?
Say it again, sorry?
Friction.
Permeability is basically friction. It's frictional loss. So you have a pressure that's upstream, you have a different pressure that's downstream. If there's no friction, then the two pressures will be the same. It's frictional loss. That's exactly what it is. Yeah, it's a good question. That's relating it back to fluids. And so the bottom line is that we can get a permeability, a hydraulic conductivity. So this is hydraulic conductivity. Which is either KB bulk. KB stands for bulk permeability, which is either GB cubed over 12 nu times S, or GB cubed over 6 nu S. I guess this is for 2 fractures. This is for 1 fracture. And if you want to define it in terms of permeability, you can define it as lowercase k, which is either b cubed over 12s, or b cubed over 6s. And so we know that the units of hydraulic conductivity should be meters per second. So you can check whether that's true. It's not quite so easy because you have these difficult terms. We know that the permeability should be in units of length squared. And so length cubed over length is length squared. It's an easy one to check. And so the bottom line is, in the same way that we could define behavior for porous media in terms of pore throats, in capillary tubes, both to define capillary response and permeability. In fractures, we can do the same. We use a single fracture plate of some spacing, and we can determine what the fluid pressure, fluid height rise is if you dip that in water. We dealt that a couple of weeks ago, I'm thinking. And also now we can say something about what the permeability is. And I suppose the important thing also to mention is that almost never will we go in and try and measure the spacing, the aperture of these fractures. You wouldn't go up to the road cut on the Mount Nittany Expressway and put a feeler gauge in there. Feeler gauge is what you used to use to make the, maybe you still do, make the gap between a spark plug in a car a specific separation, little shim of metal that you put in it. You wouldn't measure the aperture because it's very difficult to measure it. But what you could do, pardon me, is if you did a pumping test, you could measure the permeability in situ, which is representative of some relatively big scale, maybe meters or tens of meters volume. And if you knew what the hydraulic conductivity or the permeability was, it's quite easy to measure what the spacing is between them. On the Nittany Expressway, it might be half a meter between them. It might be a meter, it might be 10 centimeters, but certainly you can measure it from looking at the outcrop or looking at core. So if you have a measurement of the permeability and you know what the spacing is, then you can immediately get some idea of the magnitude of this aperture. And the value of that is, if you know what the aperture is, then you can say something about what the other characteristics of it are in terms of its capillary behavior, because we know that the capillary response is proportional to the aperture somehow. Right? So that's the one of the reasons for doing this. The other thing, I suppose, is if you know what the permeability is to start with, and you can calculate what the initial aperture is, then if you do something to that system, like heat it up by putting nuclear waste in a mountain that makes all the blocks expand and compress the fractures, then if you know from the mechanics of what's going on how the fractures will compact, then you could calculate what the changes in permeability and characteristics of capillary behavior would change as a system as well. So you can use it as a fundamental change in the system. So that's the second thing that we might try and do here. And so we've said something about linking the magnitudes of permeabilities to the geometry of what a fracture is. And so we now know how to calculate what those permeabilities and where those might come from. You never have to derive those, but you might like to know exactly where they come from. The other thing that we can use it for is to link the permeability and the saturation behavior of the system. And so one way to do that would be to do this. And so how do I want to do this? So if you look at the behaviors that we have, let me divide it up in this way. This is for the behavior of the fractures. And let me write over here the behaviors of the porous media. And so what we know about the permeability, so let's use the permeability. This would be for single fracture, or for bulk permeability, which we've just used here. This is what we've just derived. We know that the permeability is something like this. It turns out that if we looked at a porous medium, we can also define, we could derive it if we wanted to, we can define the permeability as something like porosity times the pore diameter squared over 96. Won't derive it. If you look back in one of the earlier videos, you'd see a derivation. I'm not sure that we need to do that. But the important behavior is that we've defined this permeability as a function of some characteristic of the porous medium, the pore throat diameter or the aperture of the fracture in its spacing in this particular case. And so the benefit of that is that we could rearrange this in both of these cases. In the top case, I'm going to use blue. So we could rearrange this to be able to say that the aperture cubed is equal to, well, just by rearranging this, is equal to the bulk permeability multiplied by 12s, 12 times the spacing, which also means gives us the aperture. So we've defined in terms of the fundamental behavior in terms of the aperture as a function of permeability. If we look at the capillary behavior of this, I don't know if you remember this or not, it might be worthwhile zooming back to this. If you recall, not that, when we were talking about capillary pressure behavior, we said that we could dip a fracture into a bath of water, and the height rise within that fracture we could calculate just based on the aperture of this and the surface characteristics of surface tension, and we got a height rise which is given by this, and we could convert that into an equivalent capillary pressure just by noting that height times a unit weight is equal to a pressure. That's all. And so we have these two values for a fracture, and we also have them, by the way, for a capillary tube. We have both of those. So those are what we're relying on here. And so the basic idea is if we can calculate the permeability based on these fundamental features, idealized as they are, of the porous medium, which are a round cylindrical capillary tube or a parallel plated fracture, we can relate the aperture to the permeability, or we could relate the diameter of the pore, which is going to be equal to d squared kb 96 over porosity, and it would be the same as the square root of this. So in other words, we have the pore diameter equal to the square root of the bulk permeability divided by porosity, and I'm not sure what this is. This is supposed to be 96, not 69, but this is square root 96. If we know what the height rise in the capillary is, and I wrote down what that is, so in the porous medium the capillary pressure is equal to PC0 is equal to 4 times the diameter, no, 4 times the interfacial tension divided by the diameter. Then what we could also do is we could rearrange this in terms of the diameter, because that's our fundamental unit. And so if we do that, then the diameter would be equal to 4 times the interfacial tension divided by the capillary pressure. And so now we have the flow behavior defined relative to the diameter of the tube, and we have the capillary invasion behavior defined in the same way. And so what we could do is, you can imagine that we could equate these two to each other, and if we do that, we get something like 4 times sigma over capillary pressure is equal to permeability, the bulk permeability over the porosity, And so we could rearrange that in some way. And what we want to do is get the numbers on one side. So I'm going to leave 4 on one side. I'm going to divide both sides by square root of 96. So we lose that. And I'm going to multiply both sides by PC over sigma. So just get rid of this. And we end up with KB over porosity square root. And so this has come from our very simple models of a pore tube that is being invaded by a fluid, which gives us this expression here. Just by dipping in the fluid, how high does it ride? And how much fluid gets pushed along that little capillary tube according to the physics of that behavior. And if we look at this, well, square root 96 is about square root 100, which is about 10. So this is about 0.4, which is equal to PC over interfacial tension and permeability divided by porosity square root. And so it should hopefully look at least a little bit familiar, because if we zip back to what we talked about in maybe the second week of this our discussions, the so-called Leverett curves. Which is this curve here. This so-called J function, not sure how well you can see it, but it is J is equal to capillary pressure, difference between the non-wetting and the wetting fluid pressure, interfacial tension, permeability over porosity square root. It's this term here, if you can see it. And the magnitude at which this bubbling pressure occurs isn't actually 0.4, but it's about 0.3. And that's where that relationship comes from. It merely allows you to define the behavior in terms of invasion, of pushing fluid into it and invading progressively more and more of the pore space as you go along this curve, and defining that model based on some simple geometry, which is this tube, and comparing it with a model that looks at the same geometry and looks at the flow rates that you get once it's fully saturated, and combining them. And that's all we've done. And so we don't quite get 0.3, but we get something that's pretty close to that. It's 0.4 divided, is 4 divided by square root of 96. And so depending on exactly how you do the analysis, you end up with slightly different numbers. And so that's exactly where that relationship comes from. And so, well, maybe it's a bit mathematical, but not too much so. But the basic relationship that comes out of it is that if we do that for a fracture, we get a different relationship. It basically says that the capillary pressure is related to the permeability, or 1 over the square root permeability. So there's a relationship between them, and that's how they're linked. And so the utility of that is that it's really very difficult to measure what these entry pressures are. It's very easy to measure what permeability is. And so if you can go into the field in any way, you take a sample, take it back to the lab and measure permeability, or measure through a pump test what the large-scale permeability is in the field. If you know what the permeability is, then you can use that to be able to take the permeability. It's not so difficult to measure porosity either. If you know what the interfacial tension is, which is just a fluid characteristic that you can get from a lookup table, then all of a sudden, since we know this is at the entry pressure, then you can calculate what that entry pressure. This would, in this particular case, this would be PC0. In other words, on our little diagram that looks like this, that has a curve that looks like this magnitude here is PC0, or what we've sometimes called the bubbling pressure. And this is saturation between 0 and 1. That's it. Yes?
Are there any characteristics in where the fluid is moving through, like the material change the density as it moves across it?
The density is always, well, the density that you're using here would be the density of the liquids. And so not the, so, I mean, you could dissolve it, and that would change the bulk density. on some kind of time frame. But the density that we're using here is the density of the liquid, or the fluid actually. Could be a gas. Okay. All right. Where are we? So, it may seem a little esoteric, but it's quite important. So, if we're able to define the permeability of porous media or fractures based on some characteristic conduit, we can link the invasion characteristics, the capillary pressure saturation curves, to the flow characteristics, the relative permeability curves, and that gives us some information to be able to say what's going on. And actually your assignment, your current assignment could be thought of in terms of this. You have fractures at Yucca Mountain. Those fractures, you don't know how high a column of fluid you'd be able to support in those fractures in free behavior, right? So you're evaporating stuff, it goes up the fractures, it gets imbibed from the fractures into the material around it, but a column of this could be held within the fractures. How high would that column be? You can calculate that. If you know what the permeability of the fractures are, then you can calculate what the apertures would be. And if you know what the apertures are, you can calculate what the capillary behavior would be as well, the entry pressures. So you could calculate how much of a column of water you'd hold in there. It turns out to be very small compared to the amount that would go into the porous medium. But you can calculate that. So the other thing that we can do is, now that we know something about these behaviors that are kind of embodied in these two diagrams that sit on top of each other, then this is the flow response, the steady flow response, and this is the ability to invade and change saturations. Then we can put those concepts together and define how quickly stuff would go through the system. And for that, we can define a conservation equation, which I'll describe quickly because I think it's probably more complicated than this class warrants for this class. But then talk about the implications of that in Leverett being the same Leverett of the J function. And so this is the basic idea here. So if we want to calculate the rates at which fluid will flow in the porous medium, then what we can do is we can create a conservation equation. And the conservation equation is for mass. And it merely says that mass rate in or out plus mass rate of accumulation has to equal 0. So you have a control volume, you can think of it as differential cube, dx, dy, dz, or you can think of it as a bucket. And basically it says that the volume going into the bucket equals the volume out of the bucket minus the accumulation. If more comes out than goes in, then you're depleting it. If more goes in than comes out, then you're incrementing the storage. And that's what, in a differential form, this is the spatial change. This is the flow velocity of phase alpha. So if it's a two-phase system, then phase 1 is water, phase 2 is an apple, and we do that for each of these. This is its density, the liquid density. This is its saturation. And this is its porosity. Change in time is the rate, if you like, and this is in space. It's a rate, and of course the rate comes from the fact that it is occurs to the velocity. Velocity in, velocity out. Subtract those two velocities from each other, it's a rate of accumulation. And that's basically it. And so it probably doesn't behoove us to go into great detail in that, but the system is that typically we take this cube, differential cube, we look at how much goes in on the upstream face, how much goes out on the downstream face, which is what this x is in the x direction. And if more goes in than comes out, then we have to change the saturation, right? The porosity is not changing. The bucket's filled with sand, so there's a certain volume which is given by the volume of the bucket times the porosity. That can't change, but the saturation can change. So if more water goes in than comes out, the saturation of water has to increase. But as a consequence of that, the accumulation of the other fluid has to decrease because the two saturations can only add up to 1. And so that's what's going on. And so what we can do, to cut a long story short, is we can write this equation for the water, alpha equals 1. We can write it for the NAPL, alpha equals 2. And so we end up with 2 equations. We can substitute this velocity, which is equal to the relative permeability of phase 1 multiplied by the permeability divided by the viscosity and the change in pressure between upstream and downstream. This is Darcy's law, right? Velocity, which is our Q, relative permeability between 0 and 1, actual permeability of the sample, viscosity of the water, and the pressure gradient. If we substitute for this, then we end up with this expression here. Let's ignore this term in both cases. If we do it for the velocity of the water, Darcy's law for the water, and write it, we end up with one conservation equation, which is just this written out, after we take the densities outside the bracket. So this is multiplied by a density, and this is multiplied by a density. They cancel on both sides. If we do it then for the other fluid, which is the NAPL, we end up with that for the saturation of NAPL, etc. And so this would be density of fluid 1, and this would be the density of fluid 2. And we have 2 equations. And so we want to solve these. I've thrown this term away in both cases. And this term basically is the idea that if you think of being in a swimming pool and you look at pressure change with depth, you know that the gradient of this is given by pressure is equal to depth times unit weight. That's what this curve is here. You know in the swimming pool it's static, it's not flowing. But there's a gradient dp dx, if this is z, this is a gradient dp dz. So how come if there's a gradient of pressure and pressure occurs in Darcy's law, there's no flow? Well, the reason is because of this term that takes care of that. If we define this term in terms of heads, this term here is really a magnitude of the change in head as a function of direction. It could be z. And of course, by definition of the head, I think we talked about this in the video last time, is that with this gradient here, there's no flow because this is just a self-weight. If the gradient happened like this, then the pressure gradient is larger, and so there would be flow. There'd be flow upwards in this particular case. If the pressure gradient happens with depth happens to look like this, then it's sub-hydrostatic, and the flow of direction would be this, in a porous medium, not swimming pool. And so the fact is that the magnitude of this is the swimming pool effect, if you like. And so doesn't matter. So we end up with 2 equations, but we have 4 unknowns. The saturation of the water is changing, the saturation of the oil is changing, and also the pressure in the water can change, and the pressure in the NAPL can change. And so if we want to solve this system of equations, we can't solve for 4 variables if we have 2 equations. And so we need 2 other equations to close the system. One equation is that the saturations, by our previous definition, have to sum to 1. There can be no extra space in the system. It's either filled with water or it's filled with NAPL. There's no part of the porous medium that's not filled with anything. And so those have to satisfy this. So that's a third condition. And we also have to satisfy the capillary pressure versus saturation curves. And that is that the capillary pressure, which is just equal to the difference between the non-wetting and the wetting fluid pressures, have to actually be related in some way to the saturation. And so the difference between the two fluid pressures, in this case, we call this the water and the oil, I guess. Yeah, okay, that's right. This is the water and this is the oil. This is the wetting fluid and this is non-wetting, are related to the saturation in some way. And so this fourth term is the term that finally closes the equations. So it's not matters so much. The main point is that there's a conservation equation. It includes Darcy's law. Darcy's law is the friction that we talked about earlier. It's the frictional loss as you go from pushing it at some upstream pressure, getting it out at some lower downstream pressure. Is exactly the same as the friction that gets eaten up on the edges of a pipe as you go from upstream to downstream. And it's why the pressures upstream are larger than the downstream pressures, because you're providing work to push it downstream. So if you happen to take these four equations and you happen to solve them for a particular set of boundary conditions, then you get what are referred to as the Buckley-Leverett equations. And I'm not going to talk about the terms, but I will talk about the outcome in terms of what the flow behavior would look like. And very simply, it looks like this, if I scoot this up. So we're only really going to look at these top behaviors. So this is the idea. You're flowing water along a fracture that has two parallel faces. Actually, no, it's not a fracture, it's an aquifer. The aquifer has some thickness, which is this. It originally starts completely filled with oil. So these were developed in the 1940s to figure out what happens if you pump water into an oil reservoir that's saturated with oil to get the oil out of it. A little bit similar to our system that it could be. And so you're pumping water into this bottom face, and it goes in at some flow rate, and it's a flux of water that goes in here. So originally it's saturated with oil. We're going to allow our behavior to represent this relative permeability response. So you recognize these relative permeability curves. These are relative permeability versus saturation curves here. And we're going to satisfy these things. What these equations don't do, they don't account for capillary pressure. They assume that the capillary pressure, entry pressure, is zero. So in other words, the pressures in the oil and the water are exactly the same. So it's a simplification, and it really only works when the capillary pressure differential is small. But the whole response of this, if you look at the behavior along this line here, and the saturation as you go along here. So if you plotted, for instance, the saturation with length, x, versus the saturation of water along here, then that's exactly what this lower diagram is. So this is x along the direction of flow as you go along here, and this is the saturation on this curve here. So the reservoir starts at 0 here, so this is 0. And so what are the initial conditions that we have? Initially the reservoir sits here, and all of the reservoir is at this behavior here, right? So this is where we start. Initially in the system, there's this amount of water, and there's this amount of oil, NW. So it's an oil reservoir, 80% oil, 10% water. We know what the distributions of those in the pore spaces are. It would be what we've called pendular saturation. Sphere on sphere, there's a little ring of water around them. The rest of the pore space is filled with oil, which is this large amount here. We start pumping in water at a larger proportion, and it comes in here. So initially it'll kind of saturate this initial portion and start pushing through. So immediately the saturation jumps from this point to this point here. And after a small amount of time, the saturation distribution in here at time t1, I suppose, would look like this. Is it magenta, this color? This magenta curve here. So this region now is filled with water to this proportion here, and the amount above this would be all oil. And so we've reduced by a large amount the oil here by replacing it with water. If you go up to this point here, then still the oil is almost fully saturating the system, and only a portion is water. And as you keep on pumping this water into here at some later stage, then the saturation is going to look like this curve here. And so now the part that's water filled is all of this. And if you looked at the relative saturations at any particular point, this is the amount that is the oil, and this is the amount that is the water. It just goes like this. So if you take those expressions, 4 equations, 2 conservation equations, one for the oil, one for the water, 2 other equations that you need to put in place to be able to close the system of equations, and then solve them, then you just get a relationship that says what you'd expect. As you start syringing fluid along here, it doesn't quite 100%, if you took one pore volume up to this point here, it doesn't initially fully saturate this with water and push the oil ahead. It kind of does that. This is like a piston flow, right? If you idealize this, I suppose you could think about this as being so this would be the piston advancing, and it'd be physically going in this direction here. Behind the piston, it would be 100%, or not 100%, 80% water saturated. This would be the irreducible saturation of the oil that's left in place that you can't ever get out, and this would be the water. Ahead of this, there'd be a ton of oil at its initial saturation, and a very small amount of water. And behind this, from the front, it would be different. So there'd be these 2 boundary conditions. So that's it.